Hi there, and welcome to this lesson on Pure Mathematics 4. In this lesson, we're on Chapter 7, 7.6, and geometrical problems with vectors in 3 dimensions. We'll go straight into an example. So example 1, the 4 points given by the coordinates P, Q, R, and S describe a quadrilateral. First of all, show that PQ is parallel to SR, which means the one vector should be a multiple of the other vector, and hence prove that the quadrilateral PQRS must be a trapezium. Okay, have a go at this yourself. Pause the video, come back to me when you're ready. Okay, let's have a look. So first of all, the vector PQ is the position vector of Q. Take away the position vector of P, which is 2, 5, minus 7. The vector SR is the position vector of R. Take away the position vector of S, which gives us minus 6, minus 15, 21. To show that these vectors are parallel to each other, we need to show that one of them is a multiple of the other. Well, minus 6, minus 15, 21 is minus 3 times by the first vector. That means that the vector SR is minus 3 times by the vector PQ. It means it's 3 times as long, it is parallel, and it goes in the opposite direction. That's what the minus would mean. But the only thing that matters from our point of view is that SR is parallel to PQ, and it's not the same length. It's 3 times as long. Now, if you've got a quadrilateral and 2 of the sides are parallel but not the same length, then you must have a trapezium. Now, in the last lesson, we learned with 2-dimensional vectors, if P and Q are 2 non-parallel vectors, then if MP plus NQ equals AP plus BQ, M must equal A and N must equal B. We can just compare the coefficients of the 2 vectors. Furthermore, if we have 3 vectors, P, Q, and R, which are not on the same plane, the technical phrase for that is that they are non-coplanar vectors, then we can do the same thing again, and we can compare all 3 coefficients. A special case of this is where the vector P is just ABC, which is AI plus BJ plus CK, and the vector Q is DEF, DI plus EJ plus FK. And if P is equal to Q, then A must equal D, B must equal E, and C must equal F. Okay, let's have a look how this works out in practice. We're given the vectors S and T. First of all, we're asked to write those vectors in I, J, and K notation. And then given that the vector S equals the vector T, to find the values P, Q, and R. Have a go at this yourself, pause the video, and come back to me when you're ready. Okay, let's have a look. So first of all, just writing the vectors in I, J, and K notation. The vector S will be PQI plus Q minus 3PJ plus P plus RK, and the vector T will be 4 minus 2RI plus Q plus 2RJ minus K. And then part 2 says that given that S is equal to T, find the values of P, Q, and R. So we equate the coefficients of I, J, and K. Comparing the coefficients of I will give us PQ is equal to 4 minus 2R. Comparing the coefficients of J gives us Q minus 3P is equal to Q plus 2R. And comparing the coefficients of K gives us P plus R is equal to minus 1. Now we've just got a set of 3 simultaneous equations here that you can solve by any method you like. What I'll do is rearrange B to get that, then rearrange C to find R, and then I'll substitute 4R into equation B, which gives me minus 3P equals 2 into minus 1 minus P. Multiplying out the brackets will give me that, and solving that equation gives me P is equal to 2. Having found P, I'll then substitute that value into equation C, which gives me R equals minus 1 minus 2 when I move P to the other side. That gives me R is equal to minus 3. And now I'll substitute the value of P into equation A to find Q, which gives me 2Q equals 4 minus 2 times minus 3, which means 2Q is equal to 10 and Q is equal to 5. And that's what they asked us to do. We found P, Q, and R. Okay, example 3. It's like the examples we were doing in the last lesson in 2 dimensions, but as you'd expect, because it's in 3 dimensions, it is a great deal more confusing and quite a lot more complicated. Example 3. Prove that the lines joining the midpoints of the edges of a tetrahedron to the midpoints of the opposite edges, prove that these lines intersect at the same point and that they bisect each other. They cut each other in half. Now this needs a diagram. So we've got a tetrahedron. I'll call this vertex O the origin, makes life a lot easier if you do. And these vertices A, B, and C. They're talking about these lines from the midpoint of an edge to the midpoint of an opposite edge. That's lines like this that go from the midpoint of OC to the midpoint of AB. This one that goes from the midpoint of OA to the midpoint of BC. And finally, this one that goes from the midpoint of OB to the midpoint of AC. I'm going to call a vector from O to A, as we normally would do, as is conventional. The vector from O to B we'll call B, and the vector from O to C we'll call C. And we're going to be assuming that these diagonals do intersect at the same point, and we'll call that point where we believe they intersect the point M. Now, I'll talk you through the method for this question. It's quite long. Once I've talked you through the method, then have a go at seeing if you can actually work your way through it. First of all, we're going to have to find the three vectors that define these three diagonals. So the vector PU, the vector TR, and the vector QS, all of them in terms of the three vectors A, B, and C we've given here. Once we've done that, we are going to assume that these three vectors do meet at a point M, and then we're going to find the vector from O to M by three different routes, using each of the three diagonals, which is very similar to the examples we did in the last lesson. So first of all, to get from O to M, we're going to go from O to P and P to M. That's from O to P plus some fraction of the vector PU. And alpha is what we use for that fraction. So OP plus alpha PU. The second route we're going to take is from O to T, and then some fraction of the way along the vector from T to R, beta being the fraction in that case. And then finally from O to Q, and some fraction of the way along the vector QS, with lambda being the fraction. Now, we want these lines to intersect each other and bisect each other. What that means is we're trying to show that alpha is a half, and beta is a half, and gamma is a half, so that each of them gives M as being halfway along the relevant diagonal. Once we've got those equations, we'll have three equations in A, B, and C. We equate the coefficients in the first pair of equations to find alpha and beta. We use the third equation to find lambda, making sure that the value we find works for all of the coefficients of A, B, and C. There's a lot going on there. It takes quite a while, this. I'll let you have a go. So pause the video, try and do this, and then come back to me when you're ready. Okay, let's have a look. So first of all, we're going to find the vectors that define these three diagonals. Looking at PU first of all, the way we'll get from P to U, or I'm going to go from P to O, then from O to B, and then B to U. Doesn't matter what route you take, you should get the same answer regardless. The vector from P to O, that's minus a half of C, because I'm going backwards along it, plus B. And then the vector from B to U will be a half of the vector from B to A, because we know that that's the midpoint. And the vector from B to A is given by the position vector of A, take away the position vector of B. Multiplying out the brackets, collecting things up, gives us the vector from P to U is equal to a half A plus a half B minus a half C. Now on to the second diagonal, the vector from T to R. The route I'm going to take is from T to O, and then from O to C, and then from C to R. Doesn't matter what route you take, you should get the same answer. The vector from T to O is minus a half A. From O to C, that's just the position vector of C. And then CR is a half of the vector CB, which is a half of B minus C. Multiplying out the brackets, collecting things up, gives us the vector TR is equal to minus a half A plus a half B plus a half C. Finally, we do the same thing for the third diagonal QS. The route I'm going to take is from Q to O, and then O to C, and then C to S. QO is minus a half B. O to C is just the position vector of C. And CS is a half of the vector CA, which is a half of A minus C. Multiplying out the brackets, collecting up terms, gives me QS is equal to a half A minus a half B plus a half C. So we've done part one. Part two, we were just assuming that M is actually the point where these three diagonals meet. Now, the way we show that is by finding the vector OM by three different routes using each of the three diagonals. So first of all, I'm going to be using the diagonal PU, and the route I'm going to take from O to M is from O to P and then P to M. Well, that's from O to P plus some fraction of the vector from P to U. And that fraction I'm going to call alpha. The vector from O to P is a half C, and then PU I worked out for part one, so I've just substituted that in there. Multiplying out the brackets, collecting things together, gives me that for the vector OM. Second route I'm going to take is using the diagonal TR, and I'm going to go from O to T and then T to M, which means I've gone from O to T plus some fraction of the vector TR. And that fraction I'm going to call beta. The vector from T to R I worked out in part one, substituted in there. Multiply out the brackets, collect up terms, that will give me that. And then the third route I'm going to take is using the diagonal QS. So I'll go from O to Q and then from Q to M, which means I've gone from O to Q plus some fraction of the vector QS. And the fraction in this case I'm going to call lambda. Substituting in QS, which I found in part one, gives me that. Multiplying out the brackets, collecting together terms, gives me that for the vector OM. So we now have three equations, three different ways to find the vector OM. Be careful at this point. What we do first of all is just look at the first two equations. So they both give the route from O to M. So that means that equation one must equal equation two. That's equation one, that's equation two. Then we equate the coefficients. So first of all, looking at B, I get a half alpha must equal a half beta, which means that alpha equals beta. Looking at the coefficients of A, I've got a half alpha equals a half into 1 minus beta. Substituting alpha equals beta, I'll get a half alpha equals a half into 1 minus alpha. That gives me alpha equals a half, which is what I was hoping to get. And alpha equals beta, so beta must equal a half as well. Now, we do just need to check that these values work when we equate the coefficients of C, the third of these three vectors. So looking at the coefficients of C, a half into 1 minus alpha should equal a half beta. That gives me a half into 1 minus a half should equal a half times by a half, which gives me a quarter equals a quarter. So all is well. Therefore, we now know that the first two diagonals, they do intersect, and they do intersect at their midpoints. They bisect each other. To check the third diagonal, we need to find lambda. And the way we find lambda is by equating the third equation with either of the first two. So that's what we've done so far, finding alpha and beta, and I'm going to equate the third equation with the first one, but I could equally well equate it with the second. If I say equation 1 equals equation 3, I get that. Equating the coefficients, looking at just the coefficients for A, I'll get a half alpha is equal to a half lambda. That means alpha equals lambda. Well, we already know that alpha equals a half, so lambda as well must equal a half. Good idea just to check that all works when we look at the coefficients of b and c. So looking at the coefficient of b, I get a half alpha equals a half into 1 minus lambda. Substituting in a half for all of them gives me a quarter equals a quarter. Looking at the coefficients of c, again, if I put in a half for both of the values, I get a quarter equals a quarter, which is true, so all is well. So what have we done? We're asked to prove that the lines joining the midpoints of the edges of a tetrahedron to the midpoints of the opposite edges, that they intersect at the same point and bisect each other. We solve simultaneously the three equations, three different ways for finding OM. And by equating the coefficients, we showed that alpha does equal a half, beta does equal a half, and lambda also equals a half. Therefore, the three diagonals do intersect at their midpoints. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 120 and have a go at exercise 7F. Thanks very much for listening, and cheers.